Welcome to a world that exists just beyond what our eyes can normally see. It is a world built not from natural atoms, but from tiny, artificial structures. These structures are smaller than the wavelength of light itself. We call these amazing creations metamaterials. They are designed by scientists to have properties not found in nature. Imagine building with Legos, but on a microscopic scale. You could create materials that can bend light in strange and wonderful ways. This is the power of metamaterials. They give us a new toolbox to control the very fabric of light and energy. Now, let's add a special twist to this idea. Think about your hands. They are mirror images of each other, but you cannot perfectly stack one on top of the other. This property is called chirality. It's a fundamental feature of our universe, seen in molecules, seashells, and even galaxies. When we design metamaterials with this same handedness, we create something truly special: Chiral Metamaterials. These materials interact with light in a way that depends on its polarization, specifically whether the light itself is left-handed or right-handed. This unique ability to distinguish between different types of light opens up a universe of possibilities. Why is this so interesting? Well, light is an electromagnetic wave. It carries information and energy. Normally, materials treat all light more or less the same, but chiral metamaterials are different. They are selective. They can absorb one type of circularly polarized light while letting the other pass through completely. They can twist the light's polarization in very specific ways. This level of control is unprecedented. It's like having a special filter that can sort light based on a hidden property we couldn't easily access before. This opens the door to creating revolutionary new technologies. The magic of these materials lies in their structure. Scientists design and build tiny spirals, helices, or other twisted shapes. These shapes are carefully arranged in a repeating pattern. The size, shape, and arrangement of these tiny structures determine how the material will interact with light. By changing the design, we can tune the material's properties. We can make it work with visible light, microwaves, or other forms of electromagnetic radiation. This design-led approach allows us to engineer materials with specific functions in mind, from advanced sensors to next-generation optical computers, unlocking a new frontier in science. One of the most exciting applications for these materials is in the world of sensing. Because their interaction with light is so dependent on their precise shape, chiral metamaterials are incredibly sensitive to their surroundings. Even the slightest change in the environment can alter their structure. This alteration, in turn, changes how they affect light. This makes them perfect candidates for building highly accurate sensors. Imagine a tiny device that could tell you the exact temperature of a room just by observing a subtle shift in the color of light passing through it. This is the promise of chiral metamaterial sensors. Let's consider how this works with a simple example, like measuring humidity. A scientist could design a chiral metamaterial using a polymer that swells when it absorbs water molecules from the air. As the polymer swells, the tiny chiral structures within the material move slightly further apart. This small change in spacing is enough to alter the material's optical properties. By shining a light through the sensor and measuring the change, we can determine the exact level of humidity. This same principle can be applied to measure many other things, creating a versatile and powerful sensing platform. This concept extends far beyond just temperature and humidity. We can design these materials to respond to changes in pressure, where physical compression alters the chiral structure. They can also be used to measure the density of a surrounding liquid or gas. As the density changes, the way light travels through the medium is affected, and the chiral metamaterial registers this change with high precision. This could be incredibly useful in industrial settings, for example, to monitor chemical processes in real time without needing bulky or invasive equipment. The possibilities are truly vast. The key advantage here is the direct link between a physical change and an optical signal. There is no need for complex electronics right at the sensing point. All you need is the metamaterial itself and a light source and detector, which can be located at a safe distance. This makes these sensors ideal for use in harsh or difficult-to-reach environments. Whether it's monitoring the structural integrity of a bridge or detecting trace amounts of a specific chemical in a sample, chiral metamaterials provide a new and elegant way to observe and measure our world with remarkable sensitivity. In our everyday experience, light behaves in a very predictable way. If you shine two beams of light so they cross, they simply pass through each other without interacting. This is what we call linear optics. But under very intense light, like from a powerful laser, the rules can change. The material the light is passing through can start to behave differently. It can cause light beams to interact, change their color, or even create new beams of light. This fascinating realm is called nonlinear optics, and Chiral Metamaterials are taking it to a whole new level of control and power. The unique, twisted structure of Chiral Metamaterials makes them exceptionally good at producing these nonlinear effects. Their engineered shapes act like tiny antennas that concentrate the energy of the incoming light. This concentration dramatically enhances the material's nonlinear response. For instance, an effect called second harmonic generation, where a material doubles the frequency of light passing through it, effectively changing its color, can be thousands of times stronger in a Chiral metamaterial than in a natural crystal. This means we can achieve these effects with much less powerful lasers, making the technology more accessible. Furthermore, the shape of the Chiral structures gives us an extra knob to turn. The strength and type of the nonlinear effect can depend on the handedness of the incoming light. A metamaterial might produce a strong second harmonic signal when illuminated with left-handed light, but a very weak one when hit with right-handed light. This selectivity is a powerful tool. It allows us to build optical switches or information processors where the output depends not just on the light's intensity, but also on its polarization. This opens up new avenues for encoding and manipulating information using light. These enhanced nonlinear effects are not just a scientific curiosity. They have practical applications. Stronger nonlinear signals could lead to more efficient sources of laser light in colors that are typically difficult to produce. They could improve the sensitivity of imaging techniques used in biology, allowing scientists to see deeper into living cells with greater clarity. Ultimately, by engineering these tiny chiral structures, we are not just guiding light, we are actively changing its fundamental properties. We are becoming architects of light itself, building the foundation for the next wave of optical technologies. So far, we have discussed Chiral metamaterials as static structures, designed for a specific purpose. But what if we could change their properties on the fly? What if we could actively tune or switch their chirality? This is the frontier of research in this field, and it transforms these materials from passive optical elements into dynamic, smart devices. Scientists are developing ways to control the chiral response of these materials using a variety of external triggers. This ability to actively manipulate how a material interacts with light is a crucial step toward creating truly reconfigurable technologies. One way to achieve this is by using light itself. We can embed light-sensitive molecules into the metamaterial's structure. When we shine a control beam of light, perhaps one with a different color, onto the material, these molecules can change their shape. This change alters the overall structure of the metamaterial, thereby modifying its chiral properties. It is like having a remote control for the material's handedness. Another method involves heat. By designing a material with components that expand or contract with temperature, we can use heating or cooling to reconfigure its tiny chiral elements and change its optical response. Electricity and mechanical pressure offer even more direct control. By applying a voltage across a metamaterial made from certain liquid crystals or flexible polymers, we can cause its chiral structures to twist or reorient. This is similar to how an LCD screen on your phone or television works, but applied to these intricate, three-dimensional structures. Likewise, physically squeezing or stretching a flexible metamaterial can change the spacing and shape of its components, giving us mechanical control over its chirality. These methods allow for rapid and repeatable switching of the material's properties. Perhaps most fascinating is the use of biology to control these materials. Scientists have explored using DNA molecules as programmable building blocks. DNA is naturally chiral, and we can design custom DNA strands that fold into specific shapes or change their configuration in the presence of a particular biological signal. By integrating these DNA machines into a metamaterial, we could create sensors that optically signal the presence of a specific virus or protein. This convergence of nanotechnology and biology promises a future of incredibly smart, adaptable devices that can interact with and respond to the world in complex ways.